Okay, so, okay, if you're wondering why I'm wearing a hat, I have a corner office. My office is about like minus 20 degrees below zero, and I feel like a nice super. Should actually have my phone this. I want to say a couple things about the, I want to say one thing about the homework that's due on Friday, about the last problem. I want to give you a little push on the last problem. Then I want to do kind of a standard generic problem that you're, for photoelectric effect, and then I want to actually start getting into the Compton effect. Okay, so let's start. So, and I'll give you a hint on homework one, question. What's the last one? 5?
6.
6. Okay, so you have here's a. This is actually a sheet of metal. This is some sheet. Okay. So you have some length here like this. And you have some photons coming in like this, a beam of photons. Okay. And what do I tell you about the intensity of the light coming in?
Energy.
Okay, I mean, from the expression, what you said is correct. So this is
4,000 each.
4,000.
E
to the minus
T.
like that. First of all, let's deal with the units here. Okay, what are the units for this?
Watts per meter.
Okay, so this is going to be energy, unit time, unit area. So what is this 4,000 measured in? This is all in MKS units or SI units. So energy would be
Watts.
okay, that'd be in joule, which is going to from time is going to be second. And your area is meters squared. A joule per second is a watt. Okay, so this is your watt. So it's a watt per meter squared. This is an MKS unit. You're gonna have to kind of make one of the hard things about this problem is make certain you have everything in the same units. Okay. Now, is this light monochromatic or not monochromatic?
It's monochromatic.
It's monochromatic. So only one wavelength here. But what is this intensity doing with time? Changing. So what has to be then changed? Again, we said that this is your energy time period area. And what does that mean about radiant then? What would it be then? If this is decreasing with time. Okay, so normally what would we do? So when we had, let's say the intensity is the constant. Okay, how do we say we could write the intensity? For monochromatic light.
H times F times F.
Okay, we had an HF. What does the HF represent? Of one photon. So this is the energy of one photon. And then what did we multiply that by? Which was what?
Photons.
Yeah, the number of photons, unit time, like that. That's what we did with that. And that's all, these are a constant. Okay. Now in this case here, what has to happen now?
And it's decreasing with time.
This has to decrease as a function of time. So in our problem, problem 6, this number of photons, unit time, unit area, decreases with time. So how do you have to work that? Before I never gave the sentence that everyone's coming into my office, something like that. That was exhausting. So I'll give you the hint.
Do you just take the decaying exponential?
I can't wait to find out how to do this problem. You've all had calculus and physics 1 and physics 2, your upper level physics and engineering majors.
Let's take the derivative. How's that?
tinker with it. What's another way of writing the number of photons per unit of time? In terms of calculus.
E C photon dt.
Okay, so dn dt, where that ends gonna be the number of photons.
Hmm.
So what I'm gonna do is I can say that's your intensity, which is this I, it's your 4,000 e to the minus t. It's gonna be the energy of one photon. That's still my HF. I can still do that because that doesn't change with time. Now I'm gonna write dn dt. Now this n here is different from the other n I have. This n here is going to be your number of photons. So n equals number of photons. So tell me in terms of words, what does this then represent? This is going to be
How the number of photons changes with time.
per unit time. So it's going to be basically our number of photons per unit time here. Okay, then we have to divide this by the area, and our area here is just sort of a here. Okay. So then what can you then do with that? What does question A ask for?
After a long time.
So after a long time, how many photons are absorbed? What does a long time mean? That's a code word for
Infinity.
infinity. So what would you do for this thing?
Integrate the TL.
Put in all the, yeah, I agree, but okay. You're gonna solve for the dn. So your dn is gonna be what? It's gonna be your A, here's your HF, here's your 4,000, e to the minus t, dt like that. And then what do you have to do then? Integrate this. Now you're gonna have to be careful making certain, make certain that this unit is gonna be in terms of is measured in what? For an MKS units. HF is going to be the energy of a photon. So from an MKS unit, it's the energy of a photon better be measured in not EV, but joules. Okay. You're going to get a preposterously large number when you do this. When you work this out and you get a large number, yes, you're going to get a large number here. Okay. Why does this thing move? Does anyone know what this is the physical basis for? I have a piece of paper here or something here. I have a whole bunch of photons hitting it. They all get absorbed. What is this going to do?
Become excited.
It's going to move. Why would this move? These photons also have
Momentum.
momentum. So it becomes a conservation of momentum problem. That's the basis for a solar sail. Okay, so this is the basis for a solar sail. So there's some talk, I mean, whether this is, where people talked about this, it's actually kind of clever. It might work. They want to make a solar sail. How big do they want to make it?
They probably want to make it really small, right?
Very small. And then have a what? They have a ridiculously high-powered laser somewhere on the Earth, hit it and reflect back. And what do they want to put on that solar sail? A tiny little microchip that can take an image. And why would you want to do that? What would you love to do? We have the technology.
So that's gonna reflect or absorb.
It turns out you want it to reflect, because if it reflects, it's gonna give you a twisted kick. The conservation of angular momentum. I mean, about linear momentum. Why would you want to do that? Where? Basically, someplace other than our solar system. So what's the problem with going to another solar system? You can't travel there because your distances are too far, but some are only light years away. So what could you do? If you work this out, if it's small enough, you can accelerate this thing to get the velocities up, getting close to the speed of light. Now, that's still it's not gonna get there probably in our lifetime. But if you could do that, then what could you do? You could send these little things to some other planet, And then actually then can actually start taking images of other planets. We're not going there. Which is kind of cool. But you need a very, very high powered laser to basically hit the thing for some extended period of time. And then hope it doesn't run into something, which it probably won't. You know, that might work. It's clever. Could be garbage, but it's at least fun. That makes sense? So that's this problem here. Any questions with that? Still clear on here. I'm still clear. Let's see. Okay, I want to do an example of photoelectric. And then I'm going to do Compton scattering. Compton scattering is not hard. The physics setting it up is very easy. Then the rest of it is just there's some algebra that goes on a little while. So let's do this. So let's assume. So consider a metal with a work function of, give me a work function.
0.4 electron volts.
Is that what's from the homework?
Maybe.
Okay. And so let's say 0.1. 0.1. Here. A. What is the threshold frequency for this metal? Okay, so let's do a little review here. What is the photoelectric effect? When you take your exam, the exam questions are going to be kind of very poorly worded and kind of hard to follow and kind of incoherent. Okay, so there's going to be things like, you know, that picture. Well, whoa, what's the deal there? Okay, now what does that mean? Okay. Draw a picture of the photoelectric effect. If I were to ask you on the exam to draw a picture of the photoelectric effect, what picture would you draw?
Yeah.
Which is what? Here's your metal here. This is your metal. So here's our little electron. Hi, little electron. Okay. Then what happens? A little photon comes in here. A little gamma here. Then what happens?
The electron gets liberated.
Yeah. The electron absorbs the photon and it gets liberated. Once it's liberated, what do we call that electron? It's called the photoelectron, like this. So this is our little photoelectron. Okay, so that's our photoelectric effect. Okay, what's the physics for this? And it is this simple.
Conservation of energy.
That's conservation of energy. The initial equals E final. Okay, so what's our initial energy on this picture?
Yeah.
It's just our little electron over here. So this is HF equals. Where does that energy go?
Into the
Into the electron and
working part.
then there's some energy that it takes to get out of here. So you first has to get the electron out of here. And that's going to be your phi. That's your work function. And then the rest of the energy goes into the kinetic energy of the electron. Okay. That's what we have. That makes sense? So what did we say the threshold energy is? The threshold energy is the minimum energy
To liberate the electron.
it takes to liberate the electron, which it has to be what? Phi. So your H threshold equals phi. Okay, so we have to have this HF threshold equals phi. Okay, now tell me what could I do? I could convert the phi here to electron volts, from electron volts to joules. I can then put in, let me show you what you don't do. And it's not that it's wrong, it's just that it's painful. Okay. It's not raw. Okay, so you can say, oh, well, phi is your 0.1 EV. Okay, so you convert that to joules. What's conversion?
Multiply by, is it 1.60?
Yeah. And so 1 EV is
No, it's.
1.602 times 10 to the minus 19 joules. Okay. And then you're gonna get what? You're gonna get 0.1602 times 10 to the minus 19. Okay. Now what? You're gonna say a threshold is what? It's gonna be this phi over h. And take this phi with a 0.1602 times 10 to the minus 19 joules. And then divide it by h. And what does h equal? 6.63 times 10 to the minus 34 joule seconds. Joules go out, you're left with 1 over seconds, which are the units per hertz. So this is all perfectly fine. There's nothing wrong with that. If you do that, it's perfect. To me, I like to, when you do these things, if you can, you can't always. In number 6 in that homework, you can't. You're gonna have to convert. But if you can, try to keep everything in terms of EV and just go from there. It's gonna be a lot easier to find lambda first. And then you don't have to worry about all these other weird factors. So it is easier to find lambda first. Okay, so I have HF threshold equals phi. You tell me how to find lambda first. What is our trick?
It's happening. Multiply by 1 out of 7.
Which is what?
C over C.
C over C. This gives me HC. F over C is 1 over lambda. So this is our lambda then for the threshold. And this is phi. And so our lambda threshold is then going to be HC phi. What do you know about HC? HC is our body.
1240.
1240
40.
Okay.
EV
CP.
nanometers.
So,
Okay. What's the body phi? Our body phi is 0.1 EV. Our EVs go out, and we're left with lambda in terms of nanometers. So this is going to be 12. And then at that point, you convert that to a frequency. How do you convert that to a frequency?
Do the 1 over C over the.
C is
That.
C is F lambda. So F is C over lambda. C is
3 times.
3 times 10 to the 8 over my buddy here. 1240.
Meters.
So 1240.
Times. And
What's 10 to the negative 7?
1240 times 10 to the
minus 9.
minus 9. Okay. Here, and then that'll give you your threshold frequency. That actually, once you use it, is actually faster, and you don't have to do, okay, what is H, and now I have to convert joules to EV and blah, 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 blah. That's actually a faster way to do it. And you're less likely to make a mistake. Okay. I hope there's a part B here. It's up to you. At the frequency, at the threshold, at the frequency is tripled from part A. What is the kinetic energy of the photoelectron? So
Instead of conservation of energy,
and so that is going to be our
H of equals.
H out equals 1/2 mv squared plus phi. What stays the same? Phi stays the same because it's a function of the material that we're using. Okay, I have a couple ways. I'm probably not going to leave it like this. I'm going to do what?
HC over lambda.
Yeah, I'm going to write this as HC over lambda. And so you have 1/2 mv squared plus phi. Now, if I triple my frequency, what do I do to my wavelength? I take 1/3 of it. What does it do to this one here? So if my lambda goes to lambda, so we're at this here. So if F triples, that means that lambda goes down by. That makes sense. So what would I have here? And if I put this in here, so I'd have HC over my lambda threshold over 3, because I've tripled my frequency. And this is I'm going to take my minus 1/2. I'm not going to do that. My minus 5 over it. So this is what? This is 3 times my buddy HC over lambda threshold minus phi equals 1/2 LB squared. So we have that my buddy 1/2 LB squared equals 3 times what? I have my 1240 EV nanometers over the threshold minus my 0.1 EV, and then that'd be I know that this value here is nothing but what? Actually, there should be another zero. Not there. That's just my buddy 0.1. So this just ends up becoming 0.3, 0.1, 0.3. Okay. Part C. Find VS or part. Yeah. What's the stopping potential? Tell me why that's easy peasy. What does the stopping potential refer to as? I mean, what does it do for me?
It tells you how, like, how high the voltage has to be to stop the electron from bridging the gap, I guess.
Yep. So what we had here, remember our setup here. Remember, our experimental setup is this. That's our experimental setup. So the photon goes in, we kick up the electron here, and if this is negative enough, what's going to happen? That electron is going to zip over here, and then it's going to turn around like that, and then go back that way. And our current's going to go to 0, right? So at V sub S, the current 0. Right? And what did we show last time? We showed that this 1/2 MV squared is. Now this is nothing but E times VS. Okay. So I have the 0.2 EV equals EVS. And tell me what great thing you can do without doing any word unit conversion. Get rid of the E. Cancel the E's. The VS is 0.2. And if you remember in the derivation, this is actually a negative value. The reason it's not negative here is because of the way we set up the problem here. So even though this is a positive value here, this is really negative. But leave it like that. Does that make sense? So all I can do with these are variations on the thing. The next step after this becomes preposterously complicated. It's basically working out the quantum mechanics of it. Turns out when you work out the extreme quantum mechanical details of it, that's a little more involved. Make sense? Okay, so that ends up that topic, and now we start with Compton effect. And I alluded to on Friday. You did more than allude to it. We started that. So just a couple more things here. So what did historically, what did the photoelectric effect give us? Well, historically. Photoelectric effect supported. What did it support? Planck's hypothesis on the photon. Supported Planck's photon hypothesis. And gave a method for determining what can we determine from it? What wonderful constant? Planck's constant. That makes sense? How did that work? Can you say that?
Is you have your stopping voltage.
And so we have this equation here. And we said this is our stopping potential times E. And then we solve for V sub S. So I took the phi over here divided by E. You know, if we make a graph of this, so I graph V sub S versus F. What does that look like? Yeah, this is a straight line. And again, what Scooby-Doo, some of you don't know how to speak Scooby-Doo because you haven't had me for general physics. In terms of Scooby-Doo, what would that be?
Linear.
Linear function. Okay. And straight line would be great line. You put R's in front of things, and then let's Scooby-Doo. See, speaking a whole bunch of different languages here. Scooby-Doo is very important. Great line. Okay, so this is a right line. Okay, so what do we have? We have this guy here, and then we extend this. What does this guy here give us? Yeah, this is how we can figure out the word function here. And then if we look at what does this guy here give us? Yes. Well, they're all here.
Oh, the threshold.
This is our threshold. Oh. And what does the slope give us?
Gives you the HF.
This is H over E.
HF.
Okay. Now, so if you get the slope of this graph here, and if you know E, and this E came from a famous experiment that we're not going to go into because it's basically, it's a pain. It's a really pain to carry out. It's not, will take us away from other things that are not important. Where did E come from? The milk and oil drop experiment. E was determined by the milk and oil drop experiment. It's the first class pain to do. We've done it here before, and it hurts. I mean, it physically hurts your eyes. I always tell people get a big bottle of ibuprofen and put it right by the lab setup because you're going to go through that entire bottle by the time this lab is done. It just physically hurts your eyes. And it's very frustrating too. We don't do this one anymore. Okay, so once you get this guy here, which Millikan figured out, then you can figure out H. Okay. basically he had a little container with oil in it, he squirted it, so you get these little oil droplets. He exposed it to radiation, so now the oil drops become electrically charged. And he put on a voltage on the plates. So some of the oil drops would actually go up with the electric field, and then you turn it off, and then they'll drop. And those drops would become reach terminal velocity really, really fast, and you can set it up, and by measuring the terminal velocity, you can then figure out what the charge is. And it's one of those that's, you know, you have these drops with these drops, and they're all moving at different velocities, and some are going this way, some are going this way, some this way. They're all going all over the place. You have to find one. It's just going up and down. And you have to track it. It's about as much fun as you think that's very good. Okay. So, Compton effect. Yeah, we mentioned this on Friday. What did we say the Compton effect is? You take a photon,
Is that an electron?
shoot it at an electron or any charged particle. It's usually an electron, but it doesn't have to be. So here's an incident photon. This is E. And here is basically a, let's say, a stationary charged particle. Often an electron. But it doesn't have to be. And what happens to this? And this has some wavelength here, lambda. What do we say that's going to do? It's going to scatter. So the photon goes like this. So this is a scattered photon. This is your Compton photon. This has some wavelength here, lambda prime, and then the electron, which you normally don't worry about, goes off that way here. And then this angle here, that's theta, because you normally measure the photons. Now, what did we say happens to that? So this is the Compton effect. There's a scattering of photons off from charged particles. That's the Compton effect. Now, what did we say happens to that wavelength here? Does it get bigger or smaller?
Bigger.
Because this photon loses energy. And so lambda is greater than lambda since the photon loses energy. Okay, I'm going to give you what the equation is, and then we're going to derive it. Okay. We will see that the wavelength that lambda prime is given by lambda prime minus lambda, and it's almost always written like this, that H over MC 1 minus cosine theta. Now this value right here, what are the units for this without doing any work? What do you have to measure wavelength in terms of nanometers? In other words, this is a length. So this is the length over here. What are the units for this?
Nothing.
Nothing. So this has to have units of length or nanometers. Okay, so this has units of length and is called the Compton. Okay, so we want to set up the physics for this, and then the physics is going to be very easy. And then we just have to be very, very careful with our algebra. That makes sense? Now, for those of you who haven't had me for upper level courses, for those of you who have, this is no surprise. One thing is I want you to know where all the equations come from. And so when you take your exam, I will hold you responsible for this derivation. Because there will be no equation sheets because what will you be able to do?
You could-
You'll be able to derive all the equations that you need for any equation sheet. You are your own equation sheet. Sounds like a poem. Right. I am my own equation sheet. Through the sky I go. I do not know where the photon is. It is down below. Found. Don't know what it means, but that's okay. It's poetry. If you have to analyze a poem, how do you analyze it? They died. Okay, just go to the end and say, what does the poem mean? They died. Just that's what it means. They died. And you're probably going to be right almost all the time. They died. That's brilliant. Okay, so proof. So here's our lambda, our photon. Here's a little charge at mass of m. This is our initial. And photon goes like this. Lambda prime. Here's our buddy theta. And here's our little particle variance. Okay, what did we say the physics is of this? There's two pieces of physics.
Conservation of energy and linear momentum.
Done. Okay, so all we do is apply conservation of energy. Now, I mentioned something before. When we do the conservation of energy, we have to use the relativistic energy. So we have to do this relativistically.
What is it?
Well,
What is the
that's the E squared equation I gave you, which we have to use that for. Otherwise, it won't work. Apply conservation of energy relativistically and conservation of linear momentum. Okay, so let's set this up. Okay, so let's do E initial equals E final. You'll recall, you have a particle of mass m here, momentum p. What did I state without proof? You're going to prove this at the end of the semester. And if you'd like to see the proof beforehand, come into my general relativity class, which is Monday, Tuesday, Wednesday, Friday, and you'll see the grand glorious derivation of this.
PC squared.
MC squared.
Yeah, so PC squared quantity squared plus MC squared. Okay, so let's now apply this. So we look at our picture here, and so what's my initial energy over here? Oh, this is initial, this is. I have the energy of,
Yeah.
so we have the energy of the photon. Now, can I just leave it like that?
No.
No. Why? Because what's the initial momentum of this thing at rest? Energy of it? The momentum is 0, but guess what? It still has an energy of MC squared. So this is something new relativistically. You have to put in that. What is this term called again? The rest mass energy. So this is your initial energy. Now, what's going to happen over here? Final energy is going to be the energy of the photon prime plus, I'm going to call this an electron, although it doesn't have to be, the energy of the electron here. So this has some energy here. This has some momentum PE and some energy E like this. And this one has some energy E prime, and this one has some energy just E gamma. This will be E gamma. Does that make sense? Questions to that? Okay. Now, what do we know then about this right here? We can say that this energy over here the energy squared of the electron has to be what from this equation here? The momentum of the electron C quantity squared plus the mass of the electron C squared C. So where we get that? Does that make sense?
What did you do with the MC squared on the left side there?
This just here. It's just sits there. I'm saying that this E squared here, this EE here, is this guy here. These are two different equations.
Oh, okay,
So this guy here is this right here.
okay.
That makes sense? But these guys go, you know, with this. They're connected. And this is where, what is this E here? This is my buddy here. That makes sense? Question for that. Okay, now let's do conservation of linear momentum. And it's gonna be easier if we draw a picture of this. So we're gonna say P initial equals P final. Now tell me why that equation I just wrote through is wrong. Yeah. For those of you who ask me, I spend a lot of time doing this and I'm just putting this in there. I say, don't drop out. Linear momentum is a vector quantity. You can't do this as a scale. That's fundamentally wrong. You could say, well, that's who cares? Yeah, that's very important. Now let's do this. Let's draw a picture of this. What is P initial here? I would say draw the picture for P initial. Okay, what's the linear momentum on my body here at rest? Zero. And this is to have linear momentum going this way. So this right here, my initial momentum has to be the momentum of this initial photon. Right? And this has to equal my final momentum over here. So what is my final momentum over here? I want a cartoon picture of this. This is going to be what? It's going to be something going this way, so it's going to be this guy here. So this would be P gamma prime. Plus this PE here like this. Okay. This right here is my P final. So my P final is this P gamma prime plus PE. How do vectors add? A tip to tail. So if I were to do tip to tail from this, what is that? Here's my P gamma prime. Uh-oh, am I going off to the? Oh, I'm not. Good. Okay. Well, I'd be going off into the zones. In general zod is moving. I'm not prepared for general zod. Isn't cool. Okay, so what would this be here? If I add these two together, I'd have my P final, which is this one. What does P final have to equal?
Initial.
That's equal P initial, which is nothing but my buddy
P gamma.
P gamma. So what I have here is this picture. And have P gamma plus P gamma prime plus P E like that. Where's theta in my picture?
On the side.
Yeah, here's theta. Okay, if I clap my hands and send you back to when I was a boy, it was in 11th grade. I don't know what it is. It's probably not even tall. That has to be tall. Okay, you look at that and you say the law of cosines. So apply the law of cosines. So remember what you have for the law of cosines. If this is theta, if this is C, if this is A, if this is B. Well, C squared equals what?
A squared
A squared
plus B squared
plus B squared.
plus 2AB cos.
Okay, I like the 2, and I like the A, B, and I like the cosine of theta.
Minus.
So let's do this. So if I take this value here squared, what do I get? I get PE squared equals. At this C, this is gonna be really my magnitude of PE. This is my magnitude of P gamma, and this is my magnitude of P gamma prime. So this is this side squared, this equals what? The P gamma squared. Plus my P gamma prime squared. Minus my 2 gamma, P gamma prime. Goes to the theta. Does that make sense? Questions? Okay, we're done with the proof. Now we just have to be, the proof is, now we just have to work some magic. That's all we have to do. Now, I've done this before, so I know the easiest way to do this. So is everyone happy with the basic equations we have? We have this equation here. We have this equation here. We have this equation here. Now, there's different ways of solving them. I'm going to do what I'm going to show you the way I think is the easiest way to do it. Okay, so this is what we're going to do. We're going to multiply the momentum equation by c squared. We're going to take this equation here. I'm going to put a c squared everywhere. What do I get here? I get PEC quantity squared equals P gamma C quantity squared plus P gamma prime C quantity squared minus 2. I'm going to write this in kind of a weird fashion. I'm going to take P gamma, the C with that, and the P gamma prime, and let's do that. It's not this. All I did was multiply that by C squared. That makes sense. Now, why did I do that? What do I know about P gamma C? Apply E squared equals PC squared plus MC squared to a photon. We did this day one. What does that give me? What's the mass of a photon? Zero. Okay. The mass of a photon is 0. Just so you know, it's not that the mass of a photon is tiny. The mass of a photon has to be exactly 0. The mass of a photon isn't exactly 0. Fundamental physics rules. You do an experiment and prove that a photon has a tiny mass, Nobel Prize that year. It doesn't matter if it's 1 times 10 to the minus 64. Okay, Nobel Prize. It has to be exactly 0, otherwise fundamental particle physics hits. Particle physics hits. A collapse, actually. My statement is true. Okay, so what does that give us?
Just piece.
Yeah, this goes out, so this is E squared equals PC squared with this. In other words, the energy of a photon or any massless particle is just its momentum times c. So this becomes what? This is my initial energy of the photon squared. This is my final energy of the photon, and then this is my initial energy, and that's my final. So this gives me PEC quantity equals E gamma squared plus E gamma prime squared minus 2 E gamma prime percent of the top. Does that make sense? Now, what can I say about this fellow here? I can actually solve this guy here and put that up in here. So I can say that this is the electron, the energy of the electron squared minus the rest mass squared. So I can say that this fellow is energy of the electron squared minus PE minus MC squared equals E gamma squared. It's E gamma prime squared minus 2 E gamma nine. Does that make sense? Okay, one more step. Finish it up for me. Do I know anything about my buddy EE? My energy of the electron is the energy of the photon plus the rest mass of the electron minus the energy of the scattered photon. I put it in there. So I can take this, pop it into here. And this gives me E gamma plus MC squared minus E gamma prime plus E squared minus MC squared equals E gamma squared. It's E gamma prime squared minus 2. No, we're good. E gamma prime goes out there. Yeah, we're good. Okay, this is gonna hurt, but what do? We're held almost over. We'll only have one last quest before the dragon is slain.
Did we replace the E gamma and E gamma prime with HC over lambda?
We'll do that after we finish this quest.
Oh.
Yep.
Your minus MC squared is also.
Oh, thank you. Everyone's here, I screwed up. I copied this down here, I forgot to say that. Sorry about that. Thank you. Sadly, we have to square this out. So what's going to happen? You're going to get this squared plus this squared plus this squared. And then you're going to have twice all the cross terms. Well, you guys have to let just go. Don't give your time passport for the reason. Okay, this is gonna hurt. So if I square this, I'm gonna get this squared. I'm gonna get this squared. I'm gonna get this squared, and since this times itself, the minus sign's gonna go away. Okay, now I'm gonna get twice all the cross terms. I'm gonna get this times this twice. Okay, I'm gonna get this times this twice, and it comes into the minus sign. Okay, and then I'm gonna get this times this twice. So that's that whole thing squared. Then we minus my body here. And that equals the spell. We get a lot of nice things that can happen. And what nice thing happens?
First term.
Yeah, so this term here cancels my buddy over here. This one here cancels my buddy here.
The prime that you prime also cancel.
Yeah, my buddy here cancels my buddy here. Right, and that's all the cancellation we have. Okay. I'm going to take my friend here to this side. This gives me 2 E gamma MC squared minus 2 over this guy. MC squared E gamma prime. I'm going to take this over to the other side. 2 E gamma prime minus 2 E gamma prime goes in there. Okay, what next thing happens?
Tues.
All the twos go out. And I'm gonna pull out a MC squared on the side here. And here's an E gamma, I'm probably gonna pull that out on the side. So I kill all the twos. I'm gonna pull out an MC squared. I'm gonna pull out this guy here. Okay. L's almost over. Then I'm gonna divide through by E gamma prime here, by MC squared here. So I'm gonna take those to the other side. So I'm gonna write this as E gamma. That's E gamma prime over this. And then on this. Okay, what does this become? This divided by this is 1 over E gamma prime. Minus this divided by this is 1 over E gamma. This is 1 over MC squared. 1 minus cosine of theta. Do I know anything about E gamma? How's almost over? You're gonna say you keep saying that. Yes, but now it's true. What do you know about the energy of a photon? It's HF or
HC over lambda.
HC over lambda. So we know that. So recall. The energy of a photon is HC over the wavelength. So what does this give me? This is 1 over HC lambda prime minus 1 over HC lambda equals this. This flips up. I'll take the HC to the other side. Shazam, I am done. So this gives me lambda prime minus lambda. I take the HC to the other side because it goes to the top. When the C's go out, boom. Pretty slick. Not hard, just a lot of algebra. Okay, people look like I've just broke it. Questions to that? Notice if I had nested blackboards, could you go back and look at them? What would be the worst way to do this proof?
Anyway, but this one.
Meaning PowerPoint. Ha! Okay, so PowerPoint. Okay. I told you my standard joke, you know, when I was going through school, the joke was to have the professor come in with the notes, and the notes were all wrinkled and stuff like this, and they had, you know, no pages that were basically written 40 years ago, and they're all yellowed and stuff like this, and people would make fun of them. So what's the difference between that and PowerPoint? PowerPoint doesn't yellow. It's the same thing. Okay? Again, not become a James Bond villain, as I told you before. What I'm going to do is I'm going to be chalk finger. I'm going to get all the chalk in the entire world with all the blackboards, and only I will have them. And I'm going to release a computer virus that's going to wipe out every single one of these smart systems, all the PowerPoint stuff, any variation that's going to wipe it out. And the only way people will be able to write things, teach, with chalk, and blackboards, and I will have them all. Yes,
You do not account for whiteboards.
well, they're gonna, that's second, that's, after I want to get rid of the PowerPoint first, and these are going next. These. Again, once upon a time at Alfred, when we actually had blackboards, and let's just say there was a professor who had a box of colored chalk, big sidewalk chalk, and let's just say his blackboards looked beautiful. They were stunningly gorgeous. But perhaps when the board was erased, maybe as the dust went down on the ground, and maybe it did discolor a couple times. Now, and let's just say that maybe this well-intentioned professor had a revolt from the other professor saying, we're getting rid of all the blackboards because it's just coloring everything else, and we don't like the dust and blah, blah, blah. And this professor was a very good guy. Okay. Lost this debate, and all the blackboards were replaced along with the beautiful colored chalk, and whiteboards appeared. Just perhaps that. And not that this professor is left bitter by the experience. That's fine. I'm glad that all the blackboards were removed. And whiteboards don't really erase well. They say stain. Glad. Okay, questions of this? Okay. So what's the maximum energy loss you can have? What's the maximum energy loss that can occur? And Compton scattering. What would theta have to be?
0.
Uh,
Wait, no.
Okay, if theta equals 0 here, what's cosine of 0? 1. What is 1 minus 1? 0. Lambda prime minus sine equals 0, that means no energy loss.
90.
Okay, so we have 90 here. Cosine of 90 is 0. So we have the h, we have the 1 minus 0 is 1. So we have your hc over mc, and then that would mean that lambda prime is h over mc plus lambda. Okay. We're gonna make it bigger. Yes. Theta can be. The photon can come in and backscatter. The photon backscatters, what is the angle?
180.
180. So if the photon backscatters, that equals 180. So what are we having? We're having a photon coming in like this. This is our lambda. Here's a particle like that. And then what's happening here is that it's backscattering like this. And then this particle goes off like that. Okay. In this case here, the angle here is 180 degrees. What does that give us? So this is a lambda prime minus lambda equals h over mc. 1 minus, ooh, that's a sad, see. Cosine 180. Cosine of 180 is minus 1. Minus minus make it 2. So this gives me 2 h over mc. The lambda prime is your lambda plus 2h over mc. That would be your maximum energy loss that you can have, because that'd be the biggest wavelength you can possibly have. This is maximum lambda. Max lambda prime, so greatest energy loss. I mean energy loss of the photon. Okay. What would happen if the mass of my particles increase? What would be the difference between doing Compton scattering from an electron and Compton scattering from a photon? Okay, look back at the homework, daily homework one that I had you do. And the last question I had you calculate something. What was the last question I had you calculate?
Synergies.
For
Electron, proton. and-
electron, proton, and neutron. So in daily homework 1, you calculated it's MC squared for the electron, proton, and neutron. Okay. These are going to occur all the time. You might as well commit them to memory. What is this one in terms of MEV? This is 0.511 MeV. For a proton, 938 MeV. And for a neutron, 939.6 here MeV. Yeah. There's a reason why I'm sensitive to this. I'll tell you this perhaps later. It turns out these almost have the exact same mass, and that turns out in nuclear physics to be very important. That gives rise to a symmetry in nuclear physics called isospin. And basically, you can view the proton and neutron as the same particle, just with a different isospin. Don't worry about that. Okay, eventually I'm going to do a course in nuclear physics, and you can take that out. You can spend a long time on isospin. So this is what you have here. So effectively, what's the difference between here, order of magnitude wise? What's the ratio of these? I mean, this is basically 1,000. This is basically a half. So the proton is
2000.
about 2,000 times more massive than the electron. Okay, so if we go over here to our little friend. Okay. I have an H0 by itself. I have an M here with only one factor of C. Hey, do we know some little rule that we know above?
H needs a factor of C, M needs 2.
Now, whenever you see a factor of H, you want a factor of C with it. Whenever you have an M, you want a C squared with it. So you multiply the top and bottom by C. We're going to write this as lambda prime minus lambda equals HC over MC squared 1 minus cosine. So what's going to happen here is that this right here, this is almost a factor of 2,000 greater for a proton than an electron. So what's going to happen if you scatter the same photon from a proton or an electron? For the proton, there's almost no change in the wavelength. Right? This is so large here, this is getting pretty close to being 0 because it's a factor of 2,000. For the electron, it isn't. Okay, so if you when you're Compton scattering from electron, it's going to be a bigger effect than Compton scattering from a proton. That makes sense? Now, let's go back to irradiating our apple. So we had our apple. We want to basically increase the shelf life of it. So we bombard it with radiation. And what did we say that those photons can do? Initially, we had what? The photons were doing what? We're hitting the electrons in the atom and kicking out the electrons. And what was that doing? That was called the photoelectric effect. Now, what else can those photons do?
Kick out protons and neutrons.
It's going to be kind of hard to kick out the neutron and the proton and the actual nucleus because it's kind of out there. Okay. What it can do is actually you can have Compton scattering from the electrons now. And so what you can do, you can have a Compton scattering occurring from the electrons in the apple. And these Compton scattering electrons can go and then have something else, maybe cause a photoelectric effect, maybe cause another Compton scattering to occur. But basically, when you irradiate something with radiation, this Compton scattering is occurring all over the place, as is the photoelectric effect. these processes are occurring exactly at the same time. Okay, and that's something if you're, let's say you're doing medical radiology. That's something if you're for treating cancer, or let's say you want to do imaging, they're exposing somebody to radiation. What is that radiation doing to the body? It's doing photoelectric effect and it's doing Compton scattering. And you hope it's at a low level enough that it doesn't really cause damage. Why does radiation cause things that you messed up in your body? I was friends with a biophysicist and he explained this to me. I did not know it. It's not one bit obvious. It's kind of new. Okay, so your DNA looks like this. Okay, here's water. Okay. Radiation can come and have a water molecule and actually cause it to become charged. So let's say it becomes charged in such this. Okay. What this can do, this charged molecule can then come and hit the rungs of the ladder of your DNA. And actually, when it does that, it can actually wipe that out. It can actually wipe that out. Now that's not serious. Why is that not serious? Because your body has these incoherent chemicals that make absolutely no sense. But they basically zip up and down the ladders of your DNA repairing it. So what happens here is that if you know what this one is, it turns out you know what this one is. So there's a molecule that comes up here and can actually repair this. No harm, no foul. Okay, if you get exposed to enough radiation, what can happen? Well, you can have this part wiped out. Then you can also have this part. Now the body can't repair that. There's no way for the molecule to actually figure out what this is. And then you start, so this, start getting cancers or who knows what, or the cell dies or who knows what. That's actually what it does. Okay, questions? Okay, there's not a lot you can really do with Compton scattering other than the fact that it exists. Now, historically, what did it give us? Historically. Compton scattering. Okay. Supported two things. More. More. Basically, it supported special relativity, the E-squared thing. Basically, it supported this idea here, okay, from special relativity. So it was basically a theoretical support of basically special relativity. And what else do we get? We get another support for. Again, remember this is early on. Planck again. We get again another support for the Planck's hypothesis. And Planck's photon hypothesis. Okay. Questions? I want to mention one more thing. Then we're going to start on Friday. On Friday, we want to start doing, we're going to want to take x-rays and hit a crystal with it. We're going to get a diffraction pattern on the crystal. So I want to look at that. And what I want to do is look at that in detail. And I want to do something that's almost never done in this class. I'm doing this for the engineers and also for the physics majors as well. This is not, you won't find this in any other textbooks I had in modern physics. I'm doing something that's out there. I want to go into actually crystal structure a lot more detail. So I want to go into the whole idea of what it means to the Miller indices, which you may have studied at some level. But I want to show you how from the Miller indices, if you know what they are, and I'll set them all up. I want to set up the Bravais lattice. I want to show you how to calculate Bravais lattices. This turns out it's quite beautiful. That if you know what's going on there, you can actually determine basically the spacing between basically planes of atoms in your crystal. So when I show you basically how you can set up what are called the Bravais lattice for a crystal. Once you get the Bravais lattice, that'll naturally lead to the whole concept of Miller indices. And once you get that, we'll be able to say that, let's say you have a crystal like this. We'll do some more exciting ones like this. suppose you want to know the separation distance between those two planes, there's gonna be a way of doing it. But also, if you want to know the separation distance between these two planes, there's a way of doing it. Well, suppose instead you want to know the separation between these two planes, how do you go about it? And I want to show you exactly how that works. Okay, this actually works quite. And then we can go back and then look at X-ray again, and then actually get a lot more information on those. Is class over? Really? This argument worked last time, so I don't know why it should work now. Okay, we'll go from there. Have a good day.
Oh, no.